So this is the review session for the MLT Moku Moku math. What's the name of the book? MML book. I always just call it MML book.
MML book, I think, is fine. Yeah.
So for the MML book reading session, which is a bi-weekly, and Moku Moku is a Japanese word for like a silent study session. And what we do here is that we read for 1.5 hours for anybody who is new and doesn't know. Maybe I should point out, so the entry point is the Slack, I think, in some way. And usually in the Slack, most channels have some kind of a topic set. So here I set the Zoom thing and also some information. The other important point is, I guess, the meetup page. So meetup.com is like a service to arrange meetings or meetups, or like, hey, we have some kind of a meetup and some kind of a gathering, who wants to join? So that's a general site for that. And Machine Learning Tokyo has their own account, and they announce events there. Machine Learning Tokyo is a Tokyo-based group. I'm not sure, maybe it's, so maybe Susanna should interject here to exactly state the motto, but wait, no, I'll do it. So if you go to general and then you go to here, and yeah, you go to the starter kit. So this has a very nice GitHub page where you have all the basic things you need to know about MLT. And yeah, so you have the mission. So the mission is to democratize machine learning. So MLT is an award-winning nonprofit. Sorry, I'm not sure how to read it. Domo. Dedicated, it's basically a non-profit organization, right? Yeah. So dedicated to democratize machine learning through open education, open source, and open science. MLT supports a research and engineering community of 4,500 members. So yeah, I guess the 4,500 members also includes the non-Tokyo based and non-Japan based members. So you don't have to be in Japan to be in MLT.
Yeah, and I think we're almost 5,000 now.
Update, git commit. What we'll do today, yeah. So we'll do discussion. So I really enjoyed the discussion with Philip, and please, everybody else, if you don't understand something, interrupt and ask, like, wait, I didn't get that last part. So sometimes I speak too slowly and I become boring, but sometimes I speak too fast and people lose track. So when that happens, I mean, both of those, when it happens, please, like, encourage me, like, yeah, this is clear. And also when I'm too fast, and this is generally true for anybody who's talking about mathematics. And maybe just okay, I think that's more or less everything I wanted to say about general introduction and the session, and a little intro about myself. So I'm I'm complicated. I'm also both from Serbia and from Hungary, but I studied in Hungary at the university where they have quite high standard for mathematics. I did computer science, but with huge amount of mathematics. And then I ended up there doing my PhD and then also teaching there. And I was teaching mathematics, if you didn't guess by now. So yeah, I'm quite mathy. So in that sense, I don't know, I'm maybe very, very well suited for this or very badly suited for this. But anyway, I'm gonna try to be quite mathy in the sense, but I guess it's okay because the whole book is mathy. Does anybody else have any questions right here, right now? So, oh yes, maybe one more important thing. So if you go to the meetup page of MLT and then look at the, wait, where is, oh, Susanna, where is the summary of the, what we'll do for the math reading session? But I think it's on each of these. Wait, if I go here, will I see the page which I want to show? Because we covered now. So here in Japan, we covered. No, wait, I wish to know.
There is another blog post if you're referring to that.
Yes, I think I'm. This is it, I guess.
I think so, yeah.
Thanks. So yeah, I want to show the plan. So when, and where are we? So yeah, this is the plan, what we want to do. And where's this nice picture? Oh, this is wonderful thing. Susanna, I think you did this right. So this is excellent. So this is like where when and where we are with the sessions. So we had up until now 6-7 sessions. So basically we got to linear regression, which is chapter 9. We didn't do that yet, and I think we are like the first, because we have different time zone. We have a Indian time zone and then American time zone, I think. Am I correct, Susanna?
Americas and EMEA as well.
Yes, and they will be doing, so we already did chapter 8, and they will be doing chapter 8. The India time zone will be doing it today, and the Americans will be doing it also today, but their timeline, it will be our tomorrow, right? And so yeah, this review session is, so what we did was the first chapter of the second part, and this review session is basically the review of the first part. So all the mathy things. And I think that's basically all about the intro. Maybe one more reminder that this is the first time that we are recording the whole thing, which is nice, new and exciting, and because a lot of people asked about it. And well, I guess let's move on to the next question. I would like to know about session schedule. Yes, Mahmoud. So look at, oh wait, no, I already answered this. Yes, general topic. Yes, that's a great starting point. And then meetup. Wait, this is general. And I want to go here and then here. Oops. Okay. So I got some, not this one. I want to talk about that as well. Yes, this is. Wait, where am I asking for all the nice stuff? Oh, I removed the star from that post. It should be somewhere here. What would you like to discuss? Yes, this one. Okay, so this was Philip. Okay, I want to talk. So I think the hardest chapter was which chapter was that? 7, the probability chapter. You joined the review. Oh yes, Ritanjay, how about you taking over and allowing me to have a short break and describe a little bit about SVD? Are you up for that? Is that okay?
Yeah, I'm not sure, but okay. Like, look, the code is extremely simple.
Okay, I'm gonna do a short overview of SVD, and
yeah,
and then I'll you prepare a little bit to show off your code, and okay. And
yeah, like I'm not going to refactor my code again. You know that, right?
No, not
like it's cool for me. Like if you really wanted, if you wanted to like see the code behind it, yeah. But anyways, it's in JavaScript, by the way, so like no Python.
I would like to see it a little bit if possible, because I think I
have
exactly. Questions about
I
that.
too. Okay.
So please prepare it. I will do a little bit of SVD now. So SVD is a very important thing. So, well, actually, not just SVD, because it's tightly. Wait, let me do it properly. So if you look at the table of contents and look at analytic geometry, linear algebra. Wait, no, Angel's it's matrix decomposition. And if you look at matrix decompositions, first you see eigenvalues and eigenvectors, and then the Cholesky decomposition. And a little bit more general version of this is the, well, no, sorry. Then you have the Eigendecomposition, and this is what I want to show. The Cholesky, no, Eigen. Yes, this is it. So where is it? Okay, so there are some matrices where you can do and you can do this. So what that means, and this is again something which is, I think, worth drawing. Where's the book? Here's the book. So D, P inverse A, P. So, so this is D, P inverse A, P. Okay, so this is the formula. I want to have this. So we say that A is it has to be a square matrix. And it's, I'm just going to write diag, which means that it's diagonizable. I'm not sure if I'm pronouncing that correctly in English. If you can write something like this, where P is, I think, a permutation matrix. And so this is a diagonal matrix. And if you rewrite this formula, you will get something like P D P inverse, because you have to multiply with P from this side, and then you have a P on this side as well. And then this disappears, and then you have a P inverse here, and a P inverse for this side. Oh, sorry, not B, but P. And here, and then this disappears. So you're left here with the A, and you're left with this on the other side. And what this means is that you have your original matrix A, which is a matrix, and it is full of elements, right? These are all numbers, okay? And then it says that it can be decomposed. I think this should be a permutation matrix. Am I correct about that? So invertible, no, it's not a permutation matrix. It's an invertible matrix. Okay, this is good enough. So, and yeah, sorry, this should be actually, this should actually be squared. So it says that you can split it up or factor it, as they say, into 3 other matrices in such a way that this is a P matrix. And this, of course, also has values everywhere. And this is the P inverse. So it's the same thing as this one, but only the inverse of the matrix. So if you would exclude this middle part, then you would get the identity matrix. But you don't exclude this middle part. Instead, you have elements only here on the diagonal, right? And everything else here is 0. So this is kind of a nice property, but this kind of applies only to square matrices, and you have to have this P, which is invertible, and this is a little bit strict. And I mean, it's nice, but if you can relax these conditions a little bit more, then it's even nicer. And you can inverse these conditions or relax these conditions a little bit more, and then you get to the SVD, which is the singular value decomposition. And so they are not exactly eigenvalues. I mean, when you have the Eigendecomposition of a matrix is a special case of singular value decomposition. Am I saying this correctly? I think I am. If I'm not, the more math inclined people should interject.
Yes, I think so.
Yeah, Eigendecomposition only works with the square matrices, whereas singular value decomposition works with.
Yes, that's what I meant. So it's a special case. So this is the SVD. So this is the same similar image I was drawing on the previous page or previous paper, and the only difference is, wait, I think I can add some extra stuff here. So the thing is that this sigma is a diagonal matrix. So you have only diagonal elements here. Okay, and everything else, so zeros here, and zeros here. So the main thing is that you have something on the left side, this one, you have something on the right side, this one, and you have something kind of diagonal in the middle. And this seems like, yeah, mathematicians doing mathy stuff, but actually it's not. It has quite a nice explanation. Let me get back to here. Wait, where is that nice picture? Oh yeah, this is my favorite picture. So this kind of explains what the singular values or the eigenvalues are. There's a nice mathy definition what is an eigenvalue and what is an eigenvector, but is there another which is better? Actually, I don't think so. No. So yeah, this is good. And let me try to zoom and then try to explain. So this is very important, and this is very machine learning related. So if you haven't been scared of by now, this is actually why you stayed. Okay. So the interesting thing is that you have a matrix A, and we want to talk about the eigenvalues and eigenvectors of matrix A. So the definition of an eigenvalue and an eigenvector is something like this. So if you have a vector P, it's going to be an eigenvector if the following thing holds, that if you multiply this, is it, wait, from which side? Does it have to be from this side, or I think it's from the other side, right? Wait, does it really matter? Does it? What's the usual way? Do I write it like this?
Yeah, and then
that will be okay, right? Yeah. So the thing is that if here this is a matrix. So this is R n times n. So this is a matrix. So the P's are both vectors. So it's R to the power of n. But this here lambda, this is just a simple number. So if you're a visual person like I am, so it looks something like this. So you have a matrix here, it's a square, right? You have a vector, which is kind of a row, right? So you have elements everywhere here, and then you have some elements here, and then you will get something like just one element, right? Times this. Okay?
Yes, it's a constant scalar.
Exactly. So, and this, even more important than that, is this drawing here. So this P, so the two eigenvectors are on this picture here are P1 and P2, and you can see that so if you take any vector which is somewhere here, so if you take any vector here and then you multiply it with A, you will get some vector, okay? And more precisely, what we're interested in is P1 and P2. And as you can see, P1 is, if you multiply it with A, you will get the same P1, only stretched a little bit. So this lambda 1 P1, it's a little bit longer than the original P1. So what's important here? So this is the same as A times P1. And maybe it should be noted that lambda 1 is greater than 1. Okay? And here, if you look at P2, so then when you multiply P2 with A, you will get this here. So this is A times P2. And it's again, same vector, so same direction, only it's stretched a little bit, but it's now like, how should I say, like it's not stretched out, but stretched in.
It's shrunk.
Shrunk, yes, thank you. It's shrunk. So that actually means that lambda 2 is probably going to be less than 1. So there are nice mathy ways to solve this, and which just give you these answers, but I don't think that's the interesting part. The interesting part is if you look at the formula which we had for, was it this one? Yeah, so this thing with the P minus 1. And actually it should be something like, yes. So this formula here, okay? So keep this in mind. So this is, if you look at, wait, I'm gonna, whoops. Just 1 second. Let me do this properly. Let me do it like so. So if you think about how this works, and now ignore all these drawings here, let me actually change the colors so that you know what I mean. You see what I mean? So if you think about what P inverse V is, so this V is a vector, then so this is and these are all square matrices, okay? And I hope everybody knows how the dimensions behave for matrix multiplication. So basically here, everything will be just n. So this will be n, so r to the power of n. And then when this one is the P inverse here, you can see my cursor, right? This is n times n, but if you multiply it like so, then this will again just be n. Okay, and then, so we have the same situation. So we have a vector of length n, or an n-dimensional vector, and then multiply again with an n by n matrix, and so on. So you can think about this as going, so you're taking V and then multiplying it with P inverse, then multiplying it with D, and then multiplying it with D. I think that will be the, yes. So exactly. So this is now the whole thing, but again, with the vectors. So the idea for the eigendecomposition is something along the line that you want, so assume that, so there's a way how to find the eigenvectors, but assume that you already know them. And so what you do by the first multiplication, you align them with the standard basis vectors. So the E1 and E2, you know, the usual like 1, 0, 0, so on, and then 0, 1, 0, and so on, right? So you align them to the eigenvectors to those vectors, and then you apply the per element scaling, and this is why you will have like a nice, so this is why you have here why you have a diagonal matrix, because you just need to stretch only in that direction, and then you rotate things back. Okay, so you basically invert what you did, so you put the directions back. And I don't know if this, so if anybody has questions about this, please ask. I'm gonna continue talking a little bit about this, but if anybody has like, so if you're not sure, think about it and then ask. So the important thing here is that this kind of defines very nicely how the transformation, so applying A, so multiplying with A, how that transformation behaves. And the idea is, for example, in this particular example, is that it will stretch things into this direction and it will shrink things in this direction. So if you apply, so imagine that you have this circle here on the left side and this is your input, and then you apply A and it will do this kind of stretching. In one direction it will stretch and make it grow, and then in the other direction it will make it sink. And then assume that you iterate this whole process and then you apply A again, but now to this circle. Then it will shrink this circle even more to this, and wait, let me try to draw something, what I imagine the result would be. I imagine that the result would be something like this. So it would be, it would shrink here even more, and it would stretch here even more. Like so. Okay, and then the next one, if you would take this as input and then apply A once more, then it would again here shrink like so, and it will grow. It would grow here like so. Does this make sense to anyone?
Looks good.
So yeah. Is it okay? So this is a very nice description of, so this, how should I explain? So this can give you a good intuition what the A matrix will do, how it will transform space in some sense. And
yeah.
Jason, yes.
Yeah, so A basically is any transformation that we did or we want to do. So essentially, we don't have an idea at first, like what is A doing. But if we do the singular SVD, it would tell us the path or the process, which are this P inverse, D, and P, that these things happen.
Yeah, instead of representing, like, if I may, instead of representing everything in A, you are decomposing it in terms of rotations and scale, which you are able to understand it more intuitively and better.
Yeah.
Than just observing the random numbers that is inside our A matrix.
This is, yes. So yeah, so rotation and scale, that's a very good description, I think. The part I was when I was looking for the words, I was trying to somehow to describe that this kind of gives a skeleton to the whole transformation. And by skeleton, I mean that instead of keeping in mind all the changes which it would produce, we can sort of think about only the eigenvectors, and they will, I'm not sure, I should review again this part, and there's a theorem about how sometimes they make a subspace or a space, and so the eigenvectors become basis vectors. And so if you take the eigenvectors, they will be nice bases which if you switch to them to use them as basis, then they would all the transformation would be easy to describe in some sense. This is
like we tend to use PCA as a pre-processing step just to make your data uncorrelated. So this might be one of the reasons, because like that correlation direction is being captured by the support vectors of like singular value decomposition.
Yeah. So I guess it's something like if you operate. So for example, if you operate here, you can see you can see my cursor, right? Where I'm pointing. Okay. So when your transformation has these eigenvalues and eigenvectors, and you are working in these directions, if these are your basis vectors, and you are expressing everything using these basis vectors, then you will always have to include a little bit of one eigenvector and also a little bit of the other eigenvector. While if you're setting the eigenvectors to be your basis vectors, then basically all of your transformations will be much nicer. So you will always know that you're just, it basically will become like scaling, I guess, in some sense. I'm not entirely sure. So this last claim is not 100%.
Yeah, to put it simply, if you have a matrix, and so the most important information that if you want to minimize the information you want to save, you can simply save the eigenvectors.
Yes.
Because they give the essential ingredients on how the transformation would happen, and how A would transform anything that you would apply A onto. So
yes.
So again, so this SVD helps us to visualize or to look at the steps that are not mentioned on what happens to A. What happens when A is applied? Say A is cooked. A is something, you're baking a cake, for example, right? You have your ingredients, and then you apply A, and then it becomes a cake, right? But you only see the cake if you only apply. If we only apply cake, we skip all these parts, this whatever three-step parts to receive the cake. So what SVD does is it tells us the steps. So
yeah, make the implicit things to explicit ones.
Yes. So for us, those are crucial informations, right? You want to know the steps. You want to know those 3 steps, and SVD tells you exactly those 3 steps on what happened. And in this visual, what it tells you is that at first, it would rotate the eigenvectors on the standard orientations, like the positive x and the positive y, or the 0, 1 vector, and the 1, 0 vector, E1, and the 0, 1 vector, E2, which is the orange one, and then apply D. So what does D does? D shrinks E2 and extends E1. So as you can see on the circle becomes an ellipse. And lastly, there's another step, last step, which is the P, and tells you that you would simply rotate that ellipsoid now. So instead of magically appearing circle, applied A to the circle becomes this ellipse magically, just like that. SVD tells you that this P minus 1, D, and P happen. And this, again, these are informations that are useful and we could manipulate. If we say you want exactly A again, the exact cooking again, right? But then you want certain features, let's say P1, to be more. So you want it to be doubled, for example, right? Longer P1. So what you do now is probably extend this D now. Instead of doing up to lambda 1, you can manipulate D to do 2 lambda 1. And then it will double it, and then just keep P as it is. And then you have now manipulated A into your liking because you knew the steps. Is that clear?
Yeah, I understand what you're saying.
Yeah.
And then, so this is actually the Eigendecomposition. So SVD is the general form of this. And the interesting thing is when you don't have only 2 dimensions, but we have, I don't know, like 100 dimensions or something like that. And then, so imagine that it might happen, and in practice it actually often does happen. Now, just as this eigenvector and eigenvalue 2 shrunk this dimension too small, usually a lot of dimensions in these eigenvector bases, sort of, which are actually singular. Well, eigenvector, yeah, and singular. Are they singular vectors? I'm not sure. So, so the corresponding things, some of these dimensions kind of shrink. So if you think about this dimension here as shrinking, in practice, you won't have just 2 dimensions. You will have, I don't know, maybe 100 dimensions or 1,000 dimensions. And it will often happen that, let's say, for example, if you have 100 dimensions, that 90 of those, so 90% of those will shrink to almost 0. So imagine, so this looks like here, this shrinking looks like it shrank to half, but imagine that this was really, really small lambda 2, and this basically, this ellipsoid became something like really, really flat, so almost aligned, so almost a one-dimensional thing. And now if we were doing something like 100-dimensional things, and then 90% of them almost disappear, you will be left with 10 dimensions. So basically 10 directions, or 10 dimensions. I can't really have a better word for that, which actually store some data, because the other 90% of those are of that information is shrunk to almost 0. So basically made 0 by the other singular value or eigenvalue. And this can be nicely demonstrated with the code which Mrityunjay did. And I guess I will I will pass on. Is it okay, Mrityunjay? Can you show us a little bit? Can you do a small demo?
Yeah, yes.
Okay, disabling screen share.
Can you guys see the screen?
Yep.
Yes.
Okay. So this is what I just created by the how should I say it? Gracious explanation by ML Batai. I was able to create this. So this is our original image, and this is we are applying our SVD onto this image, and this is I don't know, 2-3 months back when they have a physical meetup in Tokyo.
Yeah.
Unfortunately, I won't be able to come, of course, for some original reason. Anyways, so this is the left singular vectors. This is the singular value and right singular vectors. Quite helpful. But now the one of the queries that one might have is at this stage we are using 0 components. So first of all, let me tell you what components are. So for example, if I zoom it, all these columns represent the singular vectors, and these are indexed by the values of the singular values, right? So what does that mean? That the first singular value contains the most amount of information.
Yes, so just a short interjection. What I was explaining, that if 90% of the things are, could you, on the graph now here, which you're showing on in the middle bottom, on the pink graph. So yeah, this is, move on. So this is, now he's only showing 10% of the left data, and he's discarding almost 90% of the data, which is basically discarded anyway. And you can see that the image is almost reconstructed.
Let me do it to the 99%. As you can see, there is no difference, almost there is no difference between the original image and the reconstructed one, right? And we are still managed to do that without using the 50 or something singular vectors or singular values, which is really cool, because that is how you are able to construct the image without using that much of the information that is presented in the images, because most of them are noise.
Amazing.
So I guess
very interesting indeed. Yes,
I want to add a little bit of explanation. So could you scroll to the top, and maybe so that the a little bit back, so that the picture, yes, something like this. So the original image, no, it's okay. So you have the original image, right? So that's a black and white or a grayscale image. So that's basically a matrix. What are the dimensions of the image? How
100 by 100 pixels, I think.
100 by 100 pixels. Actually, you could have done this with so that it's not square, because SVD can be applicable for non-square images, right. But no problem. So that's just trying to give why SVD is kind of important and better. And so what you have, you do the SVD. So that's the singular value decomposition of the matrix, which we see as an image titled the original image. And when you do the SVD decomposition, you get three matrices as the result. So you have these three matrices at the top. So you have the left, the matrix on the left, you have the singular values, and you have the matrix on the right. And if you look at the singular values, you can see that's very nice. That's super nicely done. That you have, it's like a shooting star there. So you see that all the elements are on the diagonal. Everything except is on the diagonal is 0. And all the diagonals near what Mrityunjay is now showing.
Yeah.
There might be like really small values there
Yeah. Let
if you
me
have
zoom it in
absolute
and, like,
infinite
yeah.
precision,
Yeah.
but
I don't know.
generally
Like there is nothing.
it will be 0. That's because
Yes.
because you have finite precision.
Mhm.
But this is very nice. So if you cut off everything here and only leave those big values near the top left, you will have all the important information. So how that works is wait, let me think. So first, could you set the middle image to be normal? So zoom back. And you basically set everything to 0, which you don't need. So some of the diagonal elements here, starting from the bottom right corner. So for example, move your cursor more closer to the top left. So for example, not all the way, but yeah. So but don't zoom. Ah, okay. This can you leave it? Can you leave?
Okay.
Can you leave the little
Okay.
square without
Yeah.
actually zooming on it? Can you do that? Oh, okay. So yeah,
I
so
need to
something like
first
this. So
zoom
you only
it,
keep these
then.
values. Yeah. Okay. So could you do that? You hold your mouse down and so go back
What do
to
you
the
want?
original zoom.
Sorry.
Select as if you wanted to zoom, but don't let go of the mouse.
Oh, okay. You want to highlight it
like that, and keep it like that, but do it with a little bit smaller window.
From okay.
Let
So
it,
you want me to like
yes.
highlight the first 50
yes
or so? Okay.
yes
Okay. This
yes
one.
So yeah, so you leave only these values. I mean, you have most of them are 0 by default, but you leave the diagonal elements there, and you can see that you have some diagonal elements which are not selected here, and you just set them to 0. Am I correct? That's what you're doing in your code. If you're not
for
sure,
the rest of the part.
Yeah, you're setting those to 0.
Okay. So what I did, I just like when I put 15 in here or 16 in here, what I did, I just choose the first 15 singular values and the first 15 singular vectors and the first 15 rows of the right of the singular vectors, and then this product gives me this reconstructed image.
Yeah. So go up.
Yeah.
So when you say that you choose, you basically leave or wait, you don't. Do you have to leave everything the same dimension? No, you don't have to. You can basically shrink the matrix, right? So your singular values matrix becomes way smaller.
Yes.
Yeah. And maybe highlight the vectors you are using on the left matrix.
Okay. So like for example, let's
approximately
say I have 16, right? So this is
from the upper. Yes.
So
something like
I
that.
use this, and then like for example, I have 16. I just multiplied each of the values to the columns of these guys, and then I take the row of the right singular values, which gives me the constructed image which you are seeing right now, which says using component 1 to 16. So I use first 16 singular vectors and singular value. Collectively, it can be called as components. That is why I used the word component. And the 16th, like for example, so the 16th column, which then gets multiplied by the like matrix multiplication I'm talking about, multiplied by the 16th row of the right singular vectors, gives you the 16th component.
Okay. Yeah. Okay.
Yeah. So there are two ways to reconstruct our image. One of them is to go from the start and choose the 16 singular vectors and 16 singular values and multiplied by the 16 rows of the right singular vectors. That is one of the way of constructing it. another way is to just add the previously calculated singular vectors and singular values.
Okay.
Yeah, that is one of the way, and that is the way I use it.
Actually, it reminds me of the Stonehenge example that they've given in section 4.6.
That was the source.
Yeah, that was the catalyst behind this thing.
This is exactly the same thing.
Yes.
So can you show maybe some code? Ah, nice.
Yeah. So,
I wanted to ask.
This sucks, like literally.
How are you doing the SVD? Do you have some JavaScript library for SVD? Or
yes. Unfortunately, I am using not unfortunately. Okay, so in the JavaScript ecosystem, people don't really care about the scientific computing and stuff like that.
Of course.
So that is why it's getting really hard to find these libraries. So first I use the library which is known as NDJS, N-dimensional JavaScript library.
Okay.
And then I converted to the TensorFlow TF Tensor. TensorFlow JS is a really beautiful library. If anybody would like to check it out, and I fully support this library. It's beautiful. But they don't support the QR decomposition, which I don't know, they should, because it's a basis for every computational linear algebra decomposition that you can think of, right?
And how did you do the QR?
I didn't do anything. I just used this library.
Okay. From the ND, I got it.
Yeah, I first started to create my own library, and then I thought that would took me ages or something.
Exactly.
I started with LE factorization, then use householder QR factorization.
Ooh,
and
cool.
Yeah, so I thought that's going to take me ages. So
it is hard. It's way harder than it looks, and you have tools for everything. I mean, you should do that. I mean, but make it a really, really low priority, like a weekend project. When you have spare time, start coding your linear algebra routines.
My current project is to create every single algorithm that is in
that's excellent exercise.
So yeah, exactly.
Good idea,
so I don't really understand this thing until I just implemented these things. So all of these things you are seeing, these all are visualizations of LDA, so I will post it someday. I don't know. It's a bad idea to tell you guys. And now I have to be accountable for this.
Now we know. No pressure.
We are waiting.
Yes.
Okay. So this is.
I knew this was going to be a good idea. to ask Mr. J for code. Sorry, I had to.
Emil, yeah, exactly. Emil, don't meet me in real life, dude.
Why not?
Anyways, sorry. So this is pre-calculated. This is how I calculated each of the reconstructed image.
Oh,
right?
wait.
Okay. So let me go back. So I do the matrix multiplication.
I see.
Took the slice. Yeah, took the slice from. For example, if I have to reconstruct the image from 1 to 16th, right? So I'm going to take the 16th column, which is -1 and +1, as you can see. It gives me the 16th column, and slice the 16th eigenvalue, this one, okay, and then multiplied it, the simple multiplication, and then I took the matrix multiplication of the right eigenvectors, right?
I think so.
Yeah, so I took the matrix multiplication of the right eigenvectors, and then this will give me this this image, right? So this is the 16th component. And then I just add it to the image I constructed from the first to 15th eigenvectors. Like you guys are getting it, or like?
Yes.
Yeah. Okay. Sorry.
I'm
So
sure I got it.
No, all good.
yeah. So instead of wasting my computation power to take the first 15 or 16 eigenvectors again and again and again, I just took I just first calculated the 16th component. If I want to calculate the reconstructed image from 1 to 16th eigenvectors, and then just added the first to 15th eigenvectors, which I've first to 15th component reconstructed image, and then added the 16th component to it. It's just like, it's simple.
It's like it's additive in some sense.
Yeah, it's additive. Yeah, it's additive, and it protects us from calculating the exact same thing again and again and again.
Yes,
I have
wonderful.
a short suggestion. What if you say multiply, you double the first eigenvector on your middle, on the singular.
On SVD.
Yeah, on the middle one.
I'm not.
Can we?
Can you repeat it?
Can we?
Yeah. So you
like on the singular values.
So the little red dot. Don't unzoom. Say yeah. So the red dot in the middle matrix there.
Values maybe increase.
If you double that red dot.
Double one of those. And
if I double the singular values, that's what
and let's see what happened to our photo.
So so go to the place where you do
Is that quick? I don't know if what I'm asking is quick or not.
It's doable. It's doable.
Yeah, this is going to break.
Find where you're doing the SVD, and after doing the SVD, modify the output of the SVD. Where are you doing the? Yeah, yes. When you're converting it, and basically,
so
you wanna exactly.
First, let me see because I wanted to know.
So the point of this, what I'm trying to do is that what SVD gives us the power to manipulate the image or what we want to do.
So it's wait, I'm thinking about how this can be done.
Like it's simple. You have a matrix here, right? So I am just going to change the first component of that matrix.
But maybe
let me first.
If it's easier, if is it easier to just double everything on the singular values?
I think it will be doable. Wait, I'm. Oh yeah, can you? Yeah, maybe you can do it in the DevTools or whatever. Yes. And SVD.
Am I audible, guys?
Yes, you are.
Hello. Yeah, sorry.
Matrix SVD1 should, and then, so matrix SVD, yes, SVD, no S-wall, but SVD, right? Or, oh no, wait, I'm not sure.
Yeah, so now I am just going to convert the 0 to, what value are you asking for? That's the double of it, right?
Same value multiplied by 2.
Oh, multiplied by 2.
Yes,
okay.
Like that. Won't this complain that it's constant or const?
Yeah, like you are able to manipulate the array. Not just, you are not able to manipulate
the reference. Okay, got it.
Yeah, exactly.
I understand.
Yeah. Yes.
JavaScript.
It's a bit weird, I know that, but this is what we get.
I will send you a very fun video about JavaScript. If I haven't yet.
Okay, yeah, I'll be looking forward to it. Yes, like I'm pretty sure you guys are going to roast me for the rest of
No.
my life.
Oh,
Because I
this
No,
is
just
so
told you.
good.
So
Only thanks
whatever
I
you're
can get
doing,
there.
it's always good.
Yeah,
But
thank you for
if you're
sharing.
doing it, it's always
Oh,
great.
like it doesn't change a thing. Let me
Move
see
more.
the.
Mm.
Yeah,
Is it
yes, we have
saturated?
changed the singular values, but
Okay.
it doesn't change. Wow, that is strange and beautiful.
Move,
And
move,
smudge.
move.
Yeah, so this is the
Add more.
what my cooking analogy earlier was. Like you can manipulate things because now you know the steps. And
Hey, what about if we make it a negative value? Let's see. Like,
let's see.
exciting. Sorry, guys. Like, if
Yeah,
I'm
it's-
wasting
No,
your
this
time or
is
something.
super.
Let's experiment.
Exactly.
Yeah.
This is why we were torturing ourselves with mathematics for so long to see
Oh,
this.
I mean, look at this.
Yes.
This is.
Add more components. Oh, this is
Oh,
fun.
like, is this how we are going
ghost.
to negative, make the image negative or something? Oh, that
Almost.
is so cool.
I think
Oh.
I think I can explain why that happens. So basically, the big components became negative, and then the small components, the smaller details. Because if I'm not mistaken here, so the big blocks or the big surfaces are the first few components, while the small components, the small details, are the later components. And what's happening here is that it's adding the small components properly, but it starts with a very negative value for the big components.
Yeah, so when we add it over it, it's going to be negative.
If you subtract, I think you will get the negative picture.
Yeah, so this is what I'm going to do right now.
Yeah, that's...
No.
Go full.
Ooh.
Oh man,
Yes.
this is scary. Okay. Not so interesting. How about we multiply? Like it's like just playing with the Photoshop, right?
Yes.
Yeah. Okay.
Multiplication. This will be
interesting.
quirky. This will be interesting, and maybe a little bit slower.
It's going to blast it. Like let's have a bet or something, right?
No. This I'm very interested what this will be. Might be gibberish.
Yeah, it's going to blast it. Yeah, exactly.
Okay.
That's what so it's just multiplied our values. Like if you have 23 and you multiply it by 100 and you have like 23.
Everything will be just huge.
Yeah.
This means we can cover photos like that, right? And then recover it if we know what operations we did to kind of destroy it, right? So not to show people and then recover it.
Yeah, so about the recovering, I think a very important thing here to note is that this can be used for compression. So this is what I explained when before Martinjay did this. I was trying to also motivate the whole thing that this is cool because you can do compression. Because by removing, so when you have the left matrix and the right matrix, so to store the middle matrix, which is diagonal, you just need the diagonal elements. So you don't actually need to store that in a matrix. You can store it just in a vector. And of course, if you store only the first 5 or first 16, you just need 16 elements. So you don't need 100 size vector, but you need 16 long vector. And you can, when you slice the left and the right vectors, they also become way smaller than their original size. And when you add the size of the sliced or the reduced left vector and the size of the reduced right vector and the size of the reduced middle vector, middle matrix. sorry, these are all matrices, then you get a way smaller requirement than the original image had. And you will have a pretty good approximation of the original image as well.
Yeah.
And what are you doing now?
Right. Oh, I'm just playing.
I know, but what were you playing with now?
Oh, okay. So I have just take the
Square root.
I don't know. Yeah, square root of it, and like for example, in Moore-Penrose pseudo-inverse, if you have heard about it. So in Moore-Penrose pseudo-inverse, we take the inverse of the singular values, which will give us the.
Wait, where are you doing the inverse of the singular values?
Yeah, this is.
Yes. Okay.
So
okay.
this is a So I just
that will be a pseudo-inverse.
Yeah, that would be a pseudo-inverse. Now let's see the pseudo-inverse of our image. We are touching a lot of topics. Oh wow, man, that's cool.
And something is coming out, yes. And I think maybe this, I'm not sure, we should totally look this up, because this looks a little bit like, I don't know, Jason, maybe you can help, like a Laplace transform or what's that?
Oh, okay.
Or some of those filters. Doesn't this look like, or wait, not Laplace, but yes, Laplace.
Discrete Fourier, like discrete cosine transform, like it looks
maybe.
like that.
Maybe, although I'm pretty sure it's none of
I've been
those.
playing recently. Some of things that would look like that could be like if you would take a Fourier transform of a photo and then just take the face. So you can either take the magnitude, absolute value of the Fourier transform, or the face. And if you do the face, usually they would kind of look like that, because the Fourier transform would have some form which reflects the geometric features of your original photo, but the face doesn't have, and this is what, that's why we might see, but definitely this, I'm not sure what is happening.
No, of course, I mean, if you're not working with this, you won't be able to guess like so, but yeah, you have some similars. I mean, by the looks of it, I mean, it looks kind of like those transformations, but of course, it would be very brave of us to claim anything just by looking at it.
Yeah. Like you are just doing the Moore-Penrose pseudo-inverse of this image, right? So like, how can it get connected to the? Anyways, like, is there any other questions you want me guys to address regarding this visualization?
I don't know. Let's move on to the next question.
Yeah, exactly. Like I should stop my screen.
Yes, please.
Thank you so much for sharing.
Thank you very much. Yes.
Thank you very much.